Hi, this is Stu Schwartz of MasterMathMentor.com. This is video BC05. The topic is arc length and surface area. It covers the BC manual pages 25 through 27. Shown on the screen is a spiral. Suppose we were to walk along the spiral, starting at the origin and ending up at the far right side of it. How far would we walk? We approximated the area under a curve using Riemann sums and found that we can get extreme accuracy by increasing the number of rectangles, or better, trapezoids. We will now approximate the length of a curve. By length, we mean how far we would walk if we were to walk along the curve f of x from x equals a to x equals b. Shown is the graph y is equal to x squared from x is equal to 0 to x is equal to 2. It shows as a blue dashed curve. We would like to find the length of this curve. In order to do so, we can approximate it by starting at the origin and drawing a straight line to the point 1, 1, and then drawing another straight line to the point 2, 4. We can calculate the length of these lines using the Pythagorean theorem and add them up. And this would be a good approximation for the length of the curve. However, it would definitely be an under approximation, as the shortest distance between 2 points are straight lines, and y is equal to x squared is a curve. Rather than use 2 lines, let's use 4 lines. We will have points at x is equal to 0, 0.5, 1, 1.5, and 2. The lines are shown in red. The length of the line can be found using the Pythagorean theorem. So from 0 to 0.5, the length of the line is the square root of 0.5 squared plus 0.25 squared, and that is 0.559. From 0.5 to 1, the length of the line is 0.5 square root of 0.5 squared plus 0.75 squared, or 0.901. And we can continue the same pattern from 1 to 1.5. The length of the line is 1.346, and from 1.5 to 2, the length of the line is 1.82. Add up all those lengths, and we get 4.626. Again, this is a very good approximation, but it is still an under approximation of the true length of the curve. It should be obvious that if we increase the number of line segments, we improve our approximation of the curve length. As the number of line segments increases, the distance between the 2 points decreases. Let delta x represent the horizontal distance between 2 consecutive points, and let delta y represent the vertical distance between those 2 points. So the length of a curve between 2 points is approximated by the statement L is equal to the limit as delta x approaches 0 and delta y approaches 0 of the square root of delta x squared plus delta y squared. We can do some creative algebra with the square root of delta x squared plus delta y squared, as we will now show. Let's look at the expression delta x squared plus delta y squared. We can first factor out a delta x squared, and we can write that as delta x squared plus delta y squared is equal to delta x squared times the quantity of 1 plus delta y squared over delta x squared. Now, since delta y squared over delta x squared is the same thing as delta y over delta x, the whole fraction squared, we can write the expression that we just generated into the quantity 1 plus delta y over delta x squared. That quantity multiplied by delta x squared. So the length of our chord is simply the square root of that expression. And therefore, if we want all of those lines added up, it would be the summation of the square root of the quantity 1 plus delta y over delta x, quantity squared, times delta x squared. Now this next step is tricky. That is equal to the summation of the square root of 1 plus delta y over delta x squared times delta x. Notice that the delta x is now outside the radical sign. Now we know that as delta y or delta x approaches 0, delta y over delta x is equal to f prime of x. So we can say that our arc length is the summation of the square root of 1 plus f prime of x squared times delta x. And we are finally left with the length of a curve between x is equal to a and x is equal to b is L is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. This is called the arc length formula. We now have our arc length formula, which states that given a function f of x from x equals a to x is equal to b, its arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. This involves a series of steps. If you're given f of x, your first step is to find f prime of x, then square it, then add 1, then take its square root, and finally integrate it from a to b. Sometimes your expression is given as x as a function of y, and we would like to find the arc length from y equals c to y equals d. The formula is similar. The arc length is equal to the integral from c to d of the square root of 1 plus g prime of y squared dy. The technique is exactly the same. So we have, in problem 1, f of x equals 4x on the interval 0 through 3. We see the graph, which is just a straight line. We first take f prime of x and get 4. We square it and we get 16. And we add 1 to it and then take the square root. So we are interested in the integral from 0 to 3 of the square root of 1 plus 16 dx, which is x root 17 evaluated from 0 to 3, which is 3 root 17. Since the graph is a line, we can use the Pythagorean theorem to also calculate the length. And the length will be the square root of 9 plus 144, which is the square root of 153, which is also 3 root 17. Problem 2 is also a line, f of x equals 5x minus 2 on the interval negative 1 to 2. So f prime of x is 5, and f prime of x squared is 25. So the arc length is the integral from negative 1 to 2 of the square root of 1 plus 25 dx, which is x root 26 evaluated from negative 1 to 2, or 3 root 26. Finally, let's find the arc length of any general line, f of x equals mx plus k, on the interval a through b. F prime of x is m, so f prime of x squared is m squared. So our arc length is the integral from a to b of the square root of 1 plus m squared, which turns out to be x square root of 1 plus m squared, evaluated from a to b. And your answer is b minus a times the quantity of square root of 1 plus m squared. Notice that the k makes no difference because it's a constant and it just moves the curve up or down but does not affect its length. Let's look at a harder problem. F of x equals x to the 3 halves on the interval 0 through 10. Our arc length formula is shown on the right for convenience. Our first step is to take the derivative, which is 3 halves x to the 1 half, and the next step is to square it, getting 9/4 x. So our arc length is the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. We will do this with u substitution as shown on the right. U is equal to 1 plus 9x over 4. Du, therefore, is 9/4 dx. So we put a 9/4 to the right of the integral and a 4/9 to the left of the integral. We will also change the limits. So if x is equal to 0, u is equal to 1, and if x is equal to 4, u is equal to 10. So, writing this in terms of u, our arc length is 4/9, the integral from 1 to 10 of u to the 1 half du. This becomes 4/9 times 2/3 u to the 3 halves, evaluated from 1 to 10. And calculating that turns out to be 8/27, 10 to the 3 halves power minus 1, or 8/27 times the quantity 10 square root of 10 minus 1. We can verify our answer on the calculator. We can instruct the calculator to integrate the square root of 1 plus 9x over 4 from x running from 0 to 4, and we get 9.073. We also calculate 8/27 times the quantity 10 square root of 10 minus 1 and get exactly the same answer, 9.073. In number 5, you are told that at time equals 0, a bug crawls along the path f of t equals 1/3 quantity t squared plus 2 raised to the 3 halves power, where t is measured in seconds and f of t is measured in feet. We are interested in the average speed of the bug over the first 6 seconds. In order to do that, we have to figure out how far the bug traveled, and that is the arc length formula. So we start with f prime of t is equal to 3 halves times 1/3 t squared plus 2 to the 1 half power times 2t. And this gives 2t over 2 times the quantity t squared plus 2 to the 1 half power. And if we square that, we end up getting t squared quantity t squared plus 2. We now write the arc length formula. L equals the integral from 0 to 6 of t, the square root of t to the 4th plus 2t squared plus 1 dt. Now, very luckily, this thing factors into the integral from 0 to 6 of the square root of quantity t squared plus 1 quantity squared dt. And again, very luckily, the square root of a square is simply the expression itself. So our arc length is the integral from 0 to 6 of t squared plus 1 dt. This becomes t cubed over 3 plus t evaluated from 0 to 6. So the arc length is simply 216 over 3 plus 6, or 78 feet. And therefore, since it took 6 seconds to travel this distance, the average speed is 13 feet per second. Part B asks the time k, where the speed of the bug is equal to the average speed of the bug over 6 seconds. Since we were given its position function in terms of time, the velocity function is simply its derivative, which we've already calculated to be t square root of t squared plus 2. So we let k square root of k squared plus 2 equal to 13. Squaring both sides, we get k to the fourth plus 2k squared minus 169 equals 0. And using a graphic solution, we get k is equal to 3.470 seconds. Apart from the straight lines and the problems in 3, 4, and 5, which use the power of 3/2, there are actually very few problems where we can find the arc length by actually performing the integration. We can set up the integral, but actually doing the integration is another matter. However, we can perform the integration using our calculator. So for problem 6, we would like to set up the integral and then actually find the value of it using your graphing calculator, using the given interval. In 6a, we are given y equals e to the x over the interval 0 to 2. The derivative of e to the x is simply e to the x, so our integral is taken from 0 to 2 of the square root of 1 plus e to the 2x dx, and our arc length is 6.789. In b, we're given y equals tangent of x over the interval 0 to pi over 4. The derivative of tangent of x is secant squared of x. So our arc length is the integral from 0 to pi over 4 of the square root of 1 plus secant to the fourth x dx, and we get an answer of 1.278. In 6c, we're given y equals 4x minus x squared over the interval 1 to 4. The derivative is 4 minus 2x, and therefore the arc length is the integral from 1 to 4 of 1 plus quantity 4 minus 2x quantity squared. There is no need to expand this because we're using the calculator anyhow, and our answer is 6.126. Finally, 6d is y equals x sine of x over 0 to 2 pi. We have to take the derivative of that, which is x cosine of x plus sine of x. And therefore our arc length is the integral from 0 to 2 pi of the square root of 1 plus quantity x cosine of x plus sine of x quantity squared dx. Again, no need to expand that expression, and we get the arc length is 15.375. All of these problems you may choose to look at on your calculator and verify that your answers make sense. As we saw in AB calculus, if we have a curve y equals f of x in the first quadrant and rotate it about the x-axis, we get a solid of revolution. And we could calculate the volume of the solid using calculus with either the disk method or the washer method. The shape on the screen would be done with the disk method, where the radius is the function. We could also find the surface area of the shape. The surface area is how many square feet of wrapping paper we would need to wrap the shape completely. We sometimes call this the lateral surface area because it will not include the top and the bottom. The concept of surface area is not currently on the AP exam. However, we will show the formulas and how they are used. They are related to the arc length formula. If we are rotating f of x about the x-axis between x is equal to a and x is equal to b, our surface area is 2 pi integral of f of x times the square root of 1 plus f prime of x squared dx. If we are rotating g of y about the y-axis from y equals c to y equals d, our surface area is 2 pi integral from c to d of g of y times the square root of 1 plus g prime of y squared dy. Let's look at several examples. Number 7 reads f of x equals x cubed. We're looking at the interval 0 to 1, and we're going to rotate this shape about the x-axis. We start by taking the derivative, and we get 3x squared. So the derivative squared is 9x to the fourth. So using the formula, the surface area is equal to 2 pi, the integral from 0 to 1, of x cubed times the square root of 1 plus 9x to the fourth dx. Luckily, this can be integrated. If u is 1 plus 9x to the fourth, du is 36x cubed dx. We're missing the 36, so we put a 36 on the inside and divide by 36 on the outside. And we get 2 pi over 36, integral from 0 to 1 of 36x cubed, the square root of 1 plus 9x to the fourth. We are now going to change everything to u, so let's change the limits. If x is equal to 0, u equals 1. If x is equal to 1, u equals 10. So this gives us pi over 18, the integral from 1 to 10 of u to the 1/2 du, which becomes pi over 18, 2/3 u to the 3/2 evaluated from 1 to 10. And our final answer is pi over 27 times the quantity 10 to the 3/2 minus 1. In problem 8, we are rotating f of x equals the square root of x on the interval 0 to 4 about the x-axis. We start by taking f prime of x, and we get 1 over 2 square root of x. Squaring that, we get 1 over 4x. So using the formula, the surface area is equal to 2 pi, the integral from 0 to 4 of the square root of x, times the square root of 1 plus 1 over 4x dx. Using the fact that the square root of a times the square root of b is equal to the square root of ab, we can write this as 2 pi, the integral from 0 to 4 of the square root of x plus 1/4 dx. Letting u equal x plus 1/4, du is equal to dx. Let's also change the limits. If x is equal to 0, u is 1/4. If x is equal to 4, u is 17/4. So our surface area is 2 pi, the integral from 1/4 to 17/4 of u to the 1/2 du, which is 2 pi times 2/3 u to the 3/2 evaluated from 1/4 to 17/4. This is equal to 4 pi over 3 times the quantity 17 root 17 minus 1 all over 8. And the final answer, which is not pretty, pi over 6 times the quantity 17 root 17 minus 1. Problem number 9 asks to find the surface area of the sphere of radius r as shown in the picture. The graph of x squared plus y squared equals r squared graphs a circle. If we take the area above the x-axis and rotate it about the x-axis, we end up with a sphere, and that's what we would like to find the surface area of. If we solve for y, we get the square root of r squared minus x squared. Taking y prime, we get negative x over the square root of r squared minus x squared. Remember that r is a constant. And finally, r prime squared equals x squared over r squared minus x squared. Now, using our formula, the surface area is equal to 2 pi integral from negative r to r of the square root of r squared minus x squared times the square root of 1 plus x squared over r squared minus x squared dx. In the next step, we do two things. Instead of integrating from negative r to r, we can integrate from 0 to r and double our results. And realizing that the square root of a times the square root of b is equal to the square root of ab, we end up getting 4 pi integral from 0 to r of the square root of r squared minus x squared plus x squared. Finally, the last step, this difficult-looking integral, is now easy. 4 pi integral from 0 to r of r dx. The integral of r dx is rx, so we have 4 pi times rx evaluated between 0 and r, getting 4 pi r squared. This, of course, is the formula that you've always used in geometry to find the surface area of a sphere. Many formulas in geometry have been evolved from calculus.